let's start some kind of summary about the key result we obtained so far for rigid body velocity and operation. Let's review again. All right, we have a lot of reviews. Okay, so the first one I want to say, the only thing that we introduced this semester so far is the special velocity and the twist. Let me do that again, summarize all the key results you need to know. Twist by definition is omega and the V of O. This is this is the point, reference point. I call that reference point. O. It's may or may not move with the body. Okay, it's just the location of a reference point. May or may not move with the body. That's the key thing that, well, I have reviewed that many times. I hope you go back and check if you don't understand them still. So here is the angular velocity of the body, and VO is, Hongba, you say that definition again.
So VO is the velocity in the
Of what?
The reference frame thing.
The body fixed point. You have to memorize this, okay? Let's not use point. Let's particle, okay? Currently coincide with the reference point O. It's the velocity of not O, not the reference point O, is assume a body fixed particle that moves with the body currently somehow coincide with O. Okay, it's that velocity. Okay, and given that's what I emphasized or during our proof that maybe cause some confusion from some student is given the twist V, then any body fixed, other body fixed point, let's say P, its velocity is what? It's Vp equal to Vo plus omega cross from O to P this vector. Okay, that's the universal formula for the parameterization. Okay, so if you forgot how to derive things, always go back to the definition of twist and use this parameterization. You can find any body fixed point of velocity. And we derived that and discussed many times. And then we can say twist. We can define, this is so far it's coordinate free. We don't need any coordinate in order to introduce the above definitions. And we can, but we need to represent twist in frames. Okay. So suppose given frame, let's say A and B, let's say B and O with relation TBO equal to R and P. Well, I don't want to carry over those indices all over. I just say R and P here has a special meaning. Is the orientation of B in O and the origin of B in frame O. Okay, so that's these two frames. Then I can define the same vector. Sorry, I can find the coordinate of the same twist in B. Let's say first in O. In O. This is O and VOO. Okay. R, this is B. Omega B and the V, let's say B, B. So this guy, I choose the reference point to be origin of O. And this one, let's assume this BO, let's say origin of B. I can represent velocity twist either in O or in B. Okay. So then is V the velocity of B frame?
Yes.
V is a velocity, is the twist of some rigid body. I didn't say which velocity, okay, which body. It's not B. B is the frame. I want to represent this velocity. O is the frame. I want to represent this velocity. It doesn't matter. It could be V of the top, the spinning top, or V of some kind of robot and effector. But I want to represent them in O or in B. So for the did you understand what I'm trying to emphasize?
Yes.
V is a velocity. Okay, you need to know this velocity physical quantity. Now I want to represent this physical quantity in B or in O, the same physical quantity. Okay, and they are related by VO equal to the change of coordinate from B to O for twist and V of B. And we derived that in lecture 2. You should review that. This is the change of coordinate for twist. Okay. Again, this BO is nothing but adjoint operator of T BO, which by our definition here, R and P, this is nothing but R0 P skew symmetric times R, and this is R. Okay, XBO is change coordinate for twist, and this guy is a 6x6 matrix. This guy is a 6 R6 vector. Gave you another R6 vector, represent the same kind of physical quantity in different frames. Okay, let's take a break. Okay, let's continue the review. That's the twist expressed in different frames. Just want to remind you this adjoint operator, right? So if you're given for any given homogeneous matrix, let's say R and P, so the adjoint is defined as the adjoint of T is defined by this 6x6 matrix R, just about formula R and R. Okay, and we didn't discuss too much about this operator thing. It's just that we arrive at the same expression just purely based on the change of coordinate for twist. Okay, but essentially it's more abstract way to understand it is adjoint operator for twist associated with homogeneous transformation matrix T. Okay, after we introduce spatial velocity and we emphasize about screw axis, and the axis physically can be defined uniquely by three things: the direction of the axis and a point on that axis, and the pitch or the pitch, right? The linear velocity divided by the angular velocity, right? And we know there's a one-to-one correspondence between this twist and the screw axis. In this case, I think this one is just the x hat, and omega, this one is h s hat minus s hat cross q. We always assume theta dot equal to 1 when we talk about axis. Okay, and then I somehow suggested to think all rigid body motions can be thought of as screw motion. Okay, it just rotate and also traveling linearly along the same axis, right? It's rotation and the linear motion along the same axis, along the same direction or same axis. And we typically write the twist, give me arbitrary twist. I think about screw axis twist times theta dot. And this way, this guy is this kind of twist representation. And this is kind of a unit or normalized twist associated with the screw motion. Okay, that's screw axis. Then we talk about rotation operator, and exponential coordinate. They are rotation operator view is the foundation to understand exponential coordinate of SO3 and SE3. Okay, and the key here is that you need to view the rotation action or rotate this some point on the rigid body as a difference equation. So ODE for rotation, this is action, no longer orientation representation. This is a point on the rigid body. If that body is rotated about axis omega, is P dot equal to omega cross P, which is the linear function, linear differential equation. If you use skew symmetric matrix, here everything with respect to O frame. Okay, when I didn't say coordinate, it's with respect to some kind of word frame. And based on our kind of review, we know the solution to this linear differential equation in state space form is matrix exponential, the skew symmetric matrix omega t times P of 0. Okay, so if this omega, let's say equal to omega hat, which is a unit direction vector, then time just have the same kind of a unit as a degree, right? Because before it was like a speed. Now it's unit speed, it's radian per second. And so theta is T is theta, then omega hat theta. This is a rotate about omega hat by theta degree, you will have a operator. Okay, that's that kind of a description of this action can be represented by e to the omega hat theta. And this guy belongs to ISO capital ISO3. And we also introduced that little ISO3, if you still remember, that's all the skew symmetric matrices, all the things like this, where omega is in R3. All the skew symmetric matrix is little ISO3, and if you take exponential, they become capital ISO3, the orientation of the frame, rotation matrix. Let's add one more page, maybe two. Why is that? Anyway, that's fine. Next is, of course, how to understand this thing. It's if I have, this is a kind of action. It's like a verb. Okay, so if you P prime equal to E omega hat theta P, that means you have 2 points. Initially you're at P, and you take this operation, you get to another point P prime. And this is another view of the rotation matrix. And this guy is called exponential coordinate of let me say that, sorry. Omega hat theta is called exponential coordinate of R, and denoted by, or can be computed, uniquely computed by a log of R. Okay, if you give a rotation matrix, if I say log of R, it's a special log here. Okay, that gives me the exponential coordinate for which e to the omega hat theta equal to R that we're considering. Okay, now this is rotate a point. If I give a frame, let's say given a frame A, So then RA, the orientation of A is RA is XA hat, YA hat, ZA hat. Then let's say R times RA means, Hongbo, what does this mean?
We changed rotation RA to another.
No, here is action, okay?
Okay.
So this is action. This is operator. Means some action. You rotate A frame about this omega hat axis by theta degree. That's what this meaning should be. That's how you should interpret this equation, right?
Yeah.
But we also know this can be used to be as a change of coordinate as well for rotation matrix. But in this here, we think about it as a changing or this action. Okay. This means whenever you see exponential, you always think about linear differential equation that you are trying to move something, okay, about this axis, right? This means rotate. You have to know that. So I didn't review the change of coordinate perspective on rotation matrix because that's kind of simple. I only want to review the action or operator view of rotation matrix. This really means rotate RA about this axis omega hat by theta degree, for which we will get another frame, which is no longer A anymore. It's A prime or B, okay? So you move to another frame. So since this is operator, and I can, this action, for example, I can describe my action. I'm not sure whether you can see my hand or not. I rotate this pen, there's two pens, right? I rotate this pen counterclockwise about this pen axis by a certain degree. This action is a physical action. It doesn't really depend on coordinate. Okay, I can represent this action in different coordinate systems, and this action representation has both are represented by rotation matrix, but these two rotation matrix in different coordinate system can be related by the following. So expression of rotation operator R in let's say in frame O and in frame B, they are related. Let's say in O, this is in frame O, let's say it's R, then in B will be R times RB O and ROB, okay, or RB inverse. Let's say RBO inverse. Okay, this is the same operator, same kind of physical operation. This is rotation operator, same operator, same rotation operator in B. Okay, that's you need to know. And similarly, once you know rotation, and we can do, let's see, we can do homogeneous transformation. Okay. Now this is a rigid, not only a rotation, rigid body motion or operation transformation, and exponential coordinate. Very similar. It's again everything with respect to O. If I don't write down the reference frame, again, all the rigid body motion can be thought of as a screw motion. So, and the ODE to describe this screw motion is the following: is that if I have a point on the body and moves with the body, and it's body fixed point, right? For then, what is the linear velocity? Let's say this guy under a motion twist like this. What is the linear velocity of this point, body fixed point velocity?
Is V plus omega cross OP.
OP, right? And in this case, O is origin, let's say P. the coordinate of P is just the OP, okay? And this guy is, if you use homogeneous coordinate, what you have is that P tilde dot equal to, because this is skew symmetric matrix times P, right? And we have the same formula, it's like skew symmetric V 0, 0 times P tilde, okay? Which is P tilde T equal to matrix exponential of this matrix representation of twist times T and P tilde 0, okay? It's completely analogous to the rotation case. It just need to change to the homogeneous coordinate system, for which this guy is P tilde equal to P and 1, and P tilde dot is P dot and 0. Okay, and under twist, so this guy is what? This is matrix called matrix representation of the twist, and we know the little SE3 is all R6. So all the matrix representation of twist. Okay, this is the matrix representation of twist. So all the 4x4 matrix. This is 4x4, right? This is a 4x4 matrix. Okay. So from little SE3, if you have little SE3, you take exponential, you will get this guy. Okay, and that becomes this guy becomes matrix. So that's becomes let's say S. Suppose we have S had unit vector in here, and if you take exponential, this becomes exponential of S unit vector by certain degree. Let's say that, sorry, S hat theta, that's coordinate, and this is in SE3, and this is E to the S hat theta is belong to capital SE3. Okay, this is all the rotation, homogeneous transformation matrix. So S hat theta is the exponential coordinate of T, and then we can say, we can always find, okay, given me S hat theta, I can find T, which is E matrix exponential of this form. Given T, I can also find and we have a formula even for that, right? We can find the corresponding exponential coordinate, and typically we'll write it like log T. Okay, this is the log T. T is the exponential of S hat times of this form, and the log T is just giving me the exponential coordinate. Okay, again, similarly, if I have a tilted point, Hongbo, I'll ask you again, what does this mean?
So it's a translation along the
homogeneous transformation. Translation typically only have
transformation.
linear.
Yeah, transformation.
Yeah, transformation. Suppose this guy is E. Suppose this guy's matrix exponential. Sorry, his exponential coordinate is this. Is S hat times theta. Suppose this guy equal to that. Then that means you somehow apply a screw motion for this point P along the screw axis S hat by theta degree. Then you got a new point. Right, these two point now, okay, the 2 point, the coordinate, homogeneous coordinate are related by this equation. Okay, similarly, T times TA means rotate frame A. Let's say TA is the configuration of frame A. Okay, suppose that. Then this guy means rotate frame A along about the screw axis, or apply the screw motion about the screw axis s hat by theta degree. Okay, you have a frame and you rotate about the axis, but it's a screw motion, not only a pure rotation. If they have a pitch, then you also move along that axis. Okay, that's what this means. And not only that, we also derived, suppose that's a rigid operation of screw axis. Now suppose I have a screw axis S1, that's my screw axis. I think I gave that before. This is my coordinate frame. This is my screw axis S1, capital, let's say S1, and apply a screw motion. Okay, this is E to the S hat theta. Then I got another screw axis. So it's moved, right? It's moved along with the whole kind of frame. And this maybe axis becoming like this. And this may be S1 prime. So this S hat has nothing to do with this axis. All right, S hat has nothing to do with this S1. S hat is used to describe the motion or rigid transformation, rigid body transformation. And I have screw axis, let's say, physically located by in that frame here. Then I apply the screw motion defined by S hat. I will move to another screw axis, S1 prime. How does this S1 prime relate to S1? It is S1 prime equal to the adjoint of T of S1 that we derived, right? This actually means rotate about the axis S1 along screw axis S hat by theta degree. Okay, I hope that's clear now. Then, of course, expression of T, before I said everything was expressed by in frame O, expression of T in B will be what? TB inverse T times TB. Okay, where TB is the orientation, the configuration of B in frame O. Okay, that's a quick overview or review of key result. Maybe I can add today's results, right? Moving frames, velocity of moving frames, T of T. We know that this moving frame's velocity, satisfies T dot equal to, no, I would just say, let's call it V of this T equal to T dot T inverse. Okay. We have similar result for rotation matrix as well. I don't want to write all of them down because we just go over them today. Any questions so far? That's maybe 10 minutes or 15 minutes summary of almost everything we learned so far. If you have any questions regarding individual points, you need to go back to the lectures. And all of these points, bullet points, is the things I expect you to truly understand, because I have been very slow on explaining all the details, and I want you to understand every single steps I mentioned here. Okay, so then that will give you foundation to move forward. I think later on the Jacobian or kinematics of open chains. If we understand this correctly, then those things will be very simple. Okay, let's take a look at some example. Assume you can see my screen. Let's take a look at this homework 2. Let's do homework 2. That's our homework 2. And let's consider this problem. Okay. So we draw a screw axis. I'm not sure when you do your homework, I'm not sure how you draw this one. For twist this, and then try to apply some reasonable transformation for the twist. Okay, let's try to see how use MATLAB to solve this problem. I want to go over that with some detail so that you know you can somehow picture things. You can associate with geometric information in your mind, associate geometry with the math derivations. Okay, I think I somehow have a draw frame function defined. Okay, if you want to open that, draw frame. That's how I draw a frame. That's let's see the examples. Let's draw frame. Let's draw a frame, and I define a frame T1, and I can show this T1 here. Let's see that. Hold on. Let's see that. Okay, anyway, I cannot move this window. You can see there is this is the original frame, and this is the frame I draw. Okay, that's a frame T1. Now we have the homework 2 axis, which is this one, twist, and twist to screw. I think that should be a modern robotics function, and let's just use the formula we just reviewed to find the point and the direction and the pitch of that screw axis. If you compute that, let's see. Okay, let's check whether we can. Where's this point? Q is 0, 1, and -1, and there's a direction. And I can visualize this screw axis now because I know physically a point, I know a direction. I can roughly draw an arrow or a vector and see that from the whole picture. What is it? Where is my, hold on. So now you can see this, this is my screw axis, the one we visualized here. And the next question is the following. It's to, let's say we have a reasonable transformation matrix. Let's directly look at this part. Okay, let's consider a reasonable body motion. Rotate about z-axis counterclockwise by 90 degrees, and then translate along negative y-axis by 1 meter. Okay, all the axes are with respect to fixed inertial frame. So I somehow find out this is the rotation matrix by z-axis by half pi. I think we can check that, right? For example, I can run this. R will be this guy. If I take this guy, will be the rotation by z-axis by half pi, right? If you want to see that, that will be you can take a log of r, log m of r, and you find let's see. Where is my, if you take, let's write some kind of additional note here. So here we have R. If we take log, matrix log of R, suppose R is just using the x omega hat theta. Okay, if you take log, what you have is omega hat times theta. This is a skew symmetric matrix of this form, right? And this is a 3 by 3 skew symmetric matrix. And then you can also find out, extract this out of this rotation vector. So let's take a look of this. If you take log R, that's omega operation skew symmetric, which should be a skew symmetric matrix. This is the half pi thing, right? And I think modern robotics have this way to convert from little s03 to the vector itself. That's very easy. And if you run this guy again, this is the omega. It's just the, yeah, along the axis by half pi, right? So that corresponds to this rotation operator. So this R is not viewed as a change of coordinate. It's actually a what? Is the operator view, right? It's rotate about the axis by half pi. And this P is move along y direction by -1, or sorry, by 1 meter. Okay, so the overall, the homogeneous transformation is T. Okay, and what we are trying to do is find, okay, numerical values of this matrix, which is this T. That's fine. And is this true? Let's see. T, yes. And verify, no, sorry. Then I want to rotate this S to make it S prime. Okay, so I call this S prime as 1 here. Okay, so S was given by this guy, and then I applied adjoint, right? That's what we reviewed here. Okay, if you want to apply the screw motion T or rigid body motion transformation T, you apply to S, you move to S prime. So if we multiply this, we will got S1. So S1 is another, let's see, S1 is another 6 by 1 vector, tell you the new screw axis. Of course, you can from twist to the actual screw axis, and they can plot it. From the same figure, I think you see that this was the original screw axis. I rotate about this z axis by half pi. It move here, and also we somehow move it along the z direction by -1. Right. So this is the S prime we're looking for. Okay. What about screw coordinate of T? That's what trying to maybe further clarify a few concepts. And we can take log T to find the screw axis of T. And in the, well, this is a function that's written from the modern robotics kind of package. It's very easy, by the way. There's a formula there. And you can find the screw axis. Let me find it, try to print it. This is the screw axis associated with the operator T. Okay, so that's the S hat associated with the operator T, and we have three. In this case, we have three. In this case, we have 3 screw axes, right? One is the original screw axis. The other one is after the motion. After transformation, you have new screw axis. Another screw axis can be used to represent the transformation. I hope that's clear, and I will send you the code. Just go over the code with you.